introduction and inviting me to the Hsinchu in Taiwan. I was here last year, and it's like to see old friends again. I'm very happy to be here and happy to have a good time here in Hsinchu. So today I'm going to talk about the highlight lamp control circuits for automotive. So this is the students, PhD students. He do all the work. I just get to hear and present his contribution. Okay, so the paper will be presented from the introduction and some of the problem statements and methodology result, then the conclusions. So matrix LED has been used these days. This is like a display or the projector that we are using. So instead of having a single light source, people these days are trying to use a pixel headlight. There are many advantages of using the array of the LEDs. By using the arrays of LEDs, we can make certain patterns at the light. So this can be used to enhance the drive safety, and also it can be used vehicle-to-vehicle communications. So the matrix LED has multiple arrays of arrays. In this example, we have 8 LEDs connected in series, and these 8 units can be stacked together in parallel, and they can make a large size array. So in modern intelligent vehicles, there are many power-consuming parts. For electric cars, the moving motors are the most energy-consuming parts. But other than electric motors, the headlight is also quite energy-consuming, so it's good to reduce the energy consumption from the headlight. So by using the LED matrix elements, you can reduce energy compared to the halogen lamps that people used to use. So matrix LED light can be used in many different ways. This has been introduced in many leading car companies. Like for Audi, there's a car moving in one direction. So in some cases, there is an oncoming vehicle in opposite side, and we'd like to block the light, not to disturb the sight of the cars in opposite side. Also, if a car is following another car, we would like to have a light shining in the previous, the front car. So people used to use high beam and low beam controls when we're driving, but in such a case, if you cannot turn on the high beam, there are some areas might be dark, and that might be give us a condition to drive in unsafe conditions. So this is an example. This is the car that we are driving, and there is an oncoming vehicle. By using matrix LED arrays, we can block the light in this area. Also, we can block the light from the car in front of us. So it will give us more vision to the dark area at night, and also protect the other car's safety. The circuit is very simple. Basically, the conventional circuit has a shape of this. So if you look at the light circuit in the circuit on the left, for some reason the computer stopped. But if you see the circuit on the left, this is a signal. The PWM signal is supplied for this transistor, and the current will flow through this R1. Since this is a current mirror, everybody is familiar with current mirror. The current will be copied to this R2 and Q2, and by having some current flowing through the Q2, the alpha will be current flowing, there will be a IR drop. Will turn this M1 transistor on. By having this M1 transistor on, there is a bias current to LED. So if this switch is on, and this switch will deprive all the current from the LED. So if this transistor is on, then this LED will be off. So by steering currents through this M1 and LED, we can control all this. We can control this LED lights. So this simple circuit can be implemented this way for our design. If you look at the circuit on the left, this I, from the top, is the reference current. We'd like to have the same current flowing into LED through all the LEDs connected in series. But if you look at this circuit, the top current and the bottom currents are different. That's because there's additional current pass through Q2 and R4 for the bottom current parts. So to reduce the mismatch between this top current and bottom current, so we introduced additional current pass so that the additional current flowing into this switching driving current will be flow into the other pass, so that we can maintain the current through the LED are identical. So by having this design, the I in, the top current, and IP4, the bottom current, remains about constant. The way we can achieve is we introduced another bypass part. This will be the current leaking transistors, and it will copy the top currents into the bottom, so that we can maintain these currents are the same. This is because all this thing is made in array. Right, yeah. I have some difficulty with my computer. It's not working properly. Okay, thank you. Okay, so I just showed one elements of LED and gate driver. So vulnerability, there are 8 LEDs connected in series. So top currents should be the same as the bottom current, so that we can illuminate all the LEDs at the same level of light. So if one of the transistors is on, then it will produce a bypass pass, and the current will go through this transistor, then this LED will be turned off. So through this process, we need to maintain the amount of current the same. So to all this gate driver control is done by this PWM and controller. So this PWM controller has input, digital input, 8-bit digital input, and it will produce the PWM signal to on and off these transistor switches. So there are many LEDs from LED 0 to LED 7. LED 7 is the most difficult part to operate. That's because for LED 0, the reference current, the I in, is fixed value. But as we move through to the bottomwards, there are many current passes that vary this input transistor different values. So LED 7 is the most difficult part to operate. To guarantee the proper operation, we do all the simulation and do the testing. So for this gate driver, the PWM control signal is here. So once this signal is high, this trend is on. In the case, the LED is off. So this is showing so complementary on and off characteristics of LED and the transistor. So PWM signal is off, then LED will be on. Yeah, let me just stop this and start it again. Right, maybe too many things. Yeah, it's not.
It's okay.
Sorry.
No problem.
Yeah, yeah.
No problem. Or you want to copy the file to another computer?
Yeah, I have a copy of the file. Yeah.
Yeah.
Thank you.
Using my computer? Yeah, you have the file?
Yeah, thank you.
Yes. Let me try. My computer is not very good either. Oh, it's not coming out. It doesn't read. Oh, maybe this one. Yeah.
Is it okay? Is it?
Is it this one?
Right, this is the TKCAS, the top one.
Oh, TKCAS
Yeah,
one?
yeah.
Okay.
The PDF version is also available. You can open any one.
So which one?
Yeah, the top one,
The
PDF.
top one? Okay.
Maybe the computer can.
Okay, thank you. Okay, thank you.
Hopefully it works.
All right, thank you.
但是没有哎。
Yeah, it's
Okay, thank you.
It's coming. So
Yeah, it's coming here.
does it work? Running? Oh. We have 10 more minutes.
Okay. I should have done something wrong last night.
No problem.
Okay, thank you. Yeah, thank you, thank you.
Yeah, it's working.
Okay, thank you so much. Yeah, Samuel is prepared for everything. So for this design process, sorry for the delay. For this design process, we modeled LED using a Verilog A code, and we are able to program noise at the same time in this Verilog A code. There is a PWM controller. This is a comparator, digital comparator. So for this digital comparator, the B is the fixed value. The fixed value will be inputted, and A is the varying value of the digital value of varying will be compared for this fixed value, and will produce the PWM signal. So we use the D flip-flop to maintain the pulse width precisely. We use 100 megahertz for this for the clock. So there are two examples in the design stage. So high code and low code. This high code means this brighter light, and this is the dim light. So there are many drivers we can think of, from the simple gate driver to cascade current mirror gate code. For this configuration, for simple gate code, the current from this path will be copied to MP1 and will turn on and off of this switching transistor. And as a result of this switching, the amount of current flowing through this LED will be determined. Again, there will be an additional current path is made by this bias network. So since this bias currents IN and IB2 are not identical in this first design. For the second design, we can have another current path to leak this bias current out to another transistor. But in this case, since the bias variation at this node, where it says LED string voltage, is varying in a wide range. In our case, it's varying from 0 to 40 volts, and depending on the bias at this node, the current from the top and bottom are not matched very well. So we use a cascade current mirror configuration to copy the top current and bottom current more precisely. As a result, the IN and IP pole is maintained about the same level. This can be shown as a graph over here. So for this time varying, we change the conditions. So for each different part, the PWM signal are all different from high value to low value, and they're all different. In this curve, there are A, B, C cases are plotted in one graph. A is this A, B, C are plotted in one case. For C case, plotted in red, is we can guarantee a quite flat current throughout all these LEDs. While this A case, the currents are high, as high as 25%. 1 milliamps is normal current is flowing, so it can. But in A case, which is this case, the current is increased up to 25%. But by using this C configuration, we can maintain the current about the same level. So in the case of from LED 0 to LED 4, so the starting current will be maintained as a single amount, and it will come out I out. In this process, all these switches turn on and off. For this simulation, we tried all these different conditions. The worst case is happening for LED 7. The worst case is happening when all these lights are off, because when all the LEDs are off, that will introduce additional currents past to LED 7. So to test the working condition of LED 7, we try all these different conditions and make sure it's working okay. So we fabricate the chip using TSMC 0.18 micron and process. The chip size is about 2 millimeter and 1.5 millimeter in size. There are many blocks. So something large in size is a gate driver, which is a gate driver and switch and MOSFET. And we use the evaluation board to test it. We place the parallel input from PWM 0 to PWM 7. These are digital signal, and inside the chip, the PWM time domain signal was produced. And LED is placed directly on the end of the board. So we measured the pulse shape of each switching transistors. So duty cycle was measured using oscilloscope, and in this case, all this control is 8-bit. So we have from the 0 to 255 levels should be controlled. So when we measure the duty cycle, there are some variations from the smallest value to largest, the medium value. So there's ideal values are written here. So when we measure the actual duty cycle, there are a little variations. So for a PWM signal or very narrow pulse, about 0.4% was increased a little bit, but that's not much. And 8-bit resolution was maintained when we measure the duty cycle. And for this ideal duty cycle variations, we can measure the actual duty cycle values. The variations are not very large. So when we measure the duty cycle variations, so the measured duty cycle is quite small, and all these values are less than 0.35%. So we can conclude the 8-bit resolution was sort of maintained using this type of circuits. So LED was measured in various configurations. So we can turn any LEDs off and on, and we can also turn them on and in series. As a part of measurements, we measured the light intensity. This is the normalized LED brightness response. So for LED 6 and 7, so as was explained previously, LED 6 and 7 are difficult to operate because there are many current passes to join to disturb the actual current values. So when you measure current 7, there are a little variations happening in this figure. This is LED light measurements. We use the illuminator and measure the level of light intensity. But in this case, we measure there is a certain non-linearity happening in this area in LED 7. For other cases, the monotonicity was maintained. So when we measure the PWM signal, they are maintained okay. But in real light measurements, there are a little bit glitch. We attribute this as an overshoot of the input pulse in LED. So this might be another topic that we need to work on for the next run. So if we compare this work, there are many LED drivers designed previously. So we used 0.18 LED BCD process. The input voltage is varying up to 45 volt. This value is determined by the LED used. We used the gallium nitride LED. Each LED requires about 3 to 4 volts as the working voltage. Also, if you increase the current, the bias across the LED is tend to increase. We use the PWM control, and LED current can be varied up to 1 amps. And we can achieve 8-bit resolution of control. And the dimming frequency, the LED is controlled by 40 kilohertz. And if you can, so this is an 8-bit realization of the matrix headlamp set. If I conclude the presentation, so we briefly discussed the brightness control circuit with A-serial connected LEDs. If you'd like to make a large arrays, we can combine these 8 elements in vertically or horizontally. And a duty cycle can be divided into 8 bits, so 256 steps, and it was working okay. So we are able to control the LED light okay. Okay, thank you for attention.
Thank you very much, Professor Burm. Do we have any questions from the audience? Yes.
Yes.
Okay, I heard that you mentioned you used the word of A to describe your current bypass and also the gate driver circuit.
Yeah.
Is it because that you also have a digital circuit design, so you want to simulate the digital and the analog circuit all together?
Right.
And I'm just wondering how accurate you can describe your analog circuit behavior in terms of word of A when you compare with, for example, the edge spice.
Okay, so you are asking about the Verilog A modeling for LED. So during the simulation steps, LED is very difficult to model, and we realized that using Verilog A, we can express all these different components very precisely. So the level we can achieve is depending on the models, but our model is not very complicated, just use as a resistor with some tunnel voltage. And we can add some of the noise models onto it. So we think this is quite accurate to model the LED behavior. So if you like to do more steps, we can also make the models more involved, and we can, depending on how you would like to model the LED, there are level of accuracy we can achieve is possible. Yeah.
Your LED matrix, you need to generate light patterns.
Right, yeah, right.
How many light patterns do you have? How do you generate?
Right, all this is we can make all these light patterns. Currently, we are making only 1/8 LED strings, but it can be combined into a larger size by combining all these things. And all this LED can be operated independently. Is that the question? Did I answer your question? Okay.
Okay, thank you.
So,
So at the end of your talk, you mentioned about temperature sensors and some temperature sensing.
right.
Can you elaborate that a little more?
Okay, you have a very keen eye. Yeah, we also introduced temperature sensors. We didn't measure that yet, but the LED illumination is different depending on the temperature. So we'd like to calibrate the temperature variation into the light emission. That's what we would like to achieve as our next step.
Yeah, thank you so much.
Okay, thank you.
If we have no further questions, let's thank Professor Burm again.
Okay, yeah, thank you very much.